Okay, so in this lecture, we will be dealing with your steady state stability. So, how your system is stable in with respect to the steady state. But in case of the power system network, the steady state stability, we have to be worried more than the steady state stability. We have to worry about your transient stability. So that is what which defines your rigidity of the network, power system network. So for the system steady state stability, what are the parameters we have to consider? We'll be dealing with it. So you can consider the power system network. So as you know, we are converting everything into a reactance diagram. In the reactance diagram, here you can see the left side part corresponds to your generating unit, which is nothing but a generator. So that is represented in this fashion, and the right side part represents your load or nothing but your motor. So here it is a motor, is the load what you are connecting over here, and in between these two there lies the reactance of your transmission line. So this corresponds to the reactance of your transmission line. So based upon this, how can you define the steady state stability? So this steady state stability entirely involves about the power delivery to your motor. So how much amount of power delivered to the motor is the primary factor you have to consider for the steady state stability. Based upon the power delivery only, you can tell that whether the system is either it is in stable condition or it is in the unstable condition. So if maximum amount of power is delivered means you can tell that the system is stable. Or if the power is delivery is affected by some other conditions means then you cannot say that the system is in steady state stability. Okay, so this steady state stability starts from this reactance diagram, and we will be drawing the phasor diagram. After this, you have to go through this phasor diagram. So this phasor diagram you have already studied in your electrical machines. So this is nothing but you might have went through your power circle diagram and all. So the excitation EMF produced by this generator, synchronous generator, is what drawn as this phasor diagram. Okay, this blue color line there, right? So this blue color line EG is nothing but the excitation from the generator, and this IX is nothing but the drop. Okay, it is a drop across your generator to your motor. So this Ix is the voltage drop between your generator and the motor, and this X value is nothing but the additive of your all the reactances. Additive of your all the reactances. So that's it given here. X is equal to Xg plus Xc plus Xm. Xc plus Xm. So that's what given here. And then this I. So this I is nothing but the current flowing through this loop. I is the current flowing through this loop. And now you can see the excitation at the motor, that is the load voltage and the load current. The load voltage and the load current. The angle between these two will be your theta. Okay, so the load voltage and the load current angle between these two will be represented as theta, whereas the angle between angle in the sense the voltage, the phasor difference between your excited generator, the excitation of your motor is your del. So this is what we calling as rotor angle. So it is a very important thing. So this is the based upon this rotor angle only you can define the stability. So as you have already seen in the previous lecture, the stability basically depends upon the two criteria. One is your rotor angle stability, then followed by that it is your voltage stability, and followed by that it will be your frequency. We have seen that classification. So you have to know what is your rotor angle. So this rotor angle is nothing but the difference between your that is phasor difference between your generator excitation and your motor excitation. Okay, so that is what your del. So theta is nothing but the angle between the voltage and the current at the load side. Angle between the voltage and the current at the load side. Whereas this del represents the rotor angle between your excitation and your load. Okay, and so that's what here they are giving. So the excitation of the, so this is what your voltage rise. So for this loop you have to put KVL. So as per the KVL, this algebraic sum of the voltage rise is equal to the voltage drop. So here is your voltage rise, EG is equal to the voltage drop across this load XM. Okay, so that is your, this voltage, and then the drop across all the other reactances, so which is given as I into X. And here this X is equal to Xg plus Xe plus Xm. So over here you have to take this I. So I you can keep this side, and all the other things you can bring it as a single side. So it will be
So can you explain that del and theta what's range, sir?
okay. Fine, I'll be explaining. Okay. So this is the phasor diagram for the particularly the your synchronous generator. Okay, so this is what are representing. Okay, hope this is good. So here you can see this EM. So the CM is there, right? Generally, this phasor diagram is drawn with respect to the excitation from your generator. So what happens is that first you have to draw the load voltage drop. So the voltage drop over here is the drop across the motor, which is this EM. Okay, and this EM is generally we will be considering that it to be inductive. Okay, so nearly as you know that more than 75% of the industrial load will be inductive, so that this current will be lagging behind this voltage. Okay, so this angle between these two will be corresponding to your theta. Okay, whereas the excitation across your synchronous generator and then the motor will be corresponding to this del. And based upon this del, you'll be drawing this EM. After that, you'll be drawing the excitation like this EG. If you're connecting these two, in the sense, you'll be getting this voltage drop across these two, generator and motor.
Sir, excitation in the sense what do you mean?
Excitation in the sense it is a power supply. Here there will be voltage rise. Okay, so excitation in the sense it is the voltage rise. So here there will be voltage rise. That is this excitation will be basically from your power plants. It will be basically from your power plants. Okay, and from this power plants, it will be given to the load. So load in the sense it can be industrial load, or it can be your domestic load. Okay, so the connection between these two will be coming with respect to your transmission line. Okay, this will be coming with respect to your transmission line. So the power delivered or the given from this power plant has to be carried out towards the load through your transmission line. Okay, so basically this is nothing but an entire power system given in a single loop. Okay, so you can just put the KVL and you can see you'll be getting this equation. But here you have to know about the difference between the phasor difference between the supply side as well as this EM, which is the necessary for the rotor rotation of this generator. So that is what your rotor angle del. So I think you might have studied these in your electrical machines too. So there they might have covered entirely about this. Okay. I hope you got it clear, right? Now you know about what is del and theta. Shall I move on?
Yes, sir. So EM, we are just calculating the phasor difference between the generated voltage and the
And
voltage drop
the
across the motor.
across the motor. That's what your del. So that's what this angle. Okay. So if you're still having any doubt, you can just go and refer with respect to the power circle diagram of the synchronous generator, which you might have studied in electrical machines too. So in that they might have given.
Yes, sir. Yes, sir.
Okay. So after this, as I said, the steady state system stability mainly depends upon the power delivery. So as I said, you can say the system is at the steady state only when the maximum amount of power is delivered from your generator to your motor. Okay, so you have to see with respect to this power delivery. So here the power delivery P is nothing but you have to take the real part. Okay, you have to take the real part of the excitation and the current flowing through this loop. Okay, so with respect to the reactive power only, you have to take your imaginary part. If you are taking the imaginary part for this, you will be getting your reactive power. Reactive power. For the real power, you have to take only the real term, and for the apparent power, you have to combine both those things. Okay, real power as well as you have to consider your apparent uh, reactive power. You'll be getting out your apparent power. And if you're taking only the real power in the sense and real part in the sense that too particularly for that excitation and the current, so you'll be getting the equation like this. So Eg at an angle of del. So this corresponds to the excitation of your the voltage rise of your generator. Okay, and for the I, so this I, what you got over here, you have to substitute over here. The I, you have to substitute over here, and you have to take the conjugate in order to get the real part. Okay, and for this, if you are taking the conjugate in the sense very simple that all the phasors will become negated. Okay, it will become negative, and over here, if you are solving this equation, okay, so actually this equation also solving also involves multiple steps. So after the steps there will be still more than 2 to 3 steps will be there. So that also will be coming in your synchronous generator power delivery, which is in your machines too. Okay, so if you want a detailed explanation of from this step to this step, you can just go and refer that. But actually, it is a very most common equation that you might have known. The power delivery over here it will become, here it will be Eg square by x into cos 90 degree, and over here it will be minus of Eg Em by x into cos 90 plus degree. So this entire term will become eliminated, whereas this term will be there, and over here it will be cos 90 plus del, it will become minus sin del. So this is what your power delivery equation. So this you might have got with respect to your transmission and distribution. In there you might have studied in your long transmission line, you might have seen the power delivery equation. So that's the same equation what you are getting here. Okay, so here P equal to EGM by x into sin L. So this is what you'll be getting from this equation. You have to consider only the real part. For considering the imaginary part, you'll be getting the reactive power. Okay, so this is the final equation you have to know. So they will be calling this as the power delivery equation. It is EGEM by x into sin del. And from this equation, you have to get the maximum power. So how you can get the maximum power? Okay, so for that, the simple technique is you have to see the variable. So here, these remains the constant. So the variable angle will be del, and this rotor angle del, when it will be maximum. So the sine del will be maximum only when you are putting the angle to be 90 degree. This sine del will become 1. So that's what you'll be putting when del equal to rotor angle is 90 degree. Your real power delivery will be max. So it will be EGEM by X. So it is the maximum power delivery from your generator to your motor. And from this only we will be deriving your power angle curve. Okay, so this is a very important curve with respect to this unit. So here you can see the power angle curve is that plotted across the parameters power and your del, that is your rotor angle. So your power will be at your y-axis and the del will be at your x-axis. Okay, and now what you have to consider is that if you are increasing your load, so the load over here will be, if it is increased, okay, if the load is increased, what happens, your del will be increasing from 0 to pi by 2. Okay, from 0 to pi by 2, this will be increasing. This del value will be increasing, and when it reaches this del by 2, it reaches the maximum power. Okay, and after that, if the load is further starts to decrease, after it is starts to decrease, what happens, there will be decrease in your power delivery also. So now here you will be clear that how this rotor angle is affecting your power delivery. Okay, how this rotor angle is affecting the power delivery you might have got through this graph. So over here you can see another one also. In order to have a stable system, this del p by del d del, which is nothing but the slope of this graph. The slope of this graph, can get the slope of this graph very easy by plotting, by taking the tan value. If you are taking means you can get the slope of this entire graph, and for that thing, this dp by d del, if it is positive means then this system will be stable. If it is a negative means the system won't be stable. Okay, so this is a small condition. So you have to know these condition, and this graph you have to know. Very simple concept.
So can you say the condition once again, sir?
Okay, so for the power angle curve, it is the angle, it is drawn across your power as well as your del. Okay, and the first thing is, if you are increasing the load from your 0 to del by 2, okay, this is possible when your load increases. When the load increases, your del will be also increasing from 0 to pi by 2. So when it reaches the value of pi by 2, what happens, you will be getting the maximum power delivery. Okay, so after that, at this point of also the system will be stable. After that, if you're reducing the load, what happens, this del value drops down. Okay, it is just like a inverted hyperbola. And the another one particular condition for this, that the dp by d del, which is nothing but the slope of this graph, has to be positive in order to have a stable system. Okay, so it is another one condition. So here are few important points for which you can keep the system to be stable. Okay, that stable means these are if you are following these points, you can keep this slope as in a positive direction. Okay, so the points first include, you have to have a very higher excitation. The excitation has to be higher in order to maintain the stability at the steady state. And after that, the reactance, this reactance is called as this x is called as x is nothing but the summation of your generator reactance, motor reactance, and then your transmission line reactance. And this x is called as transfer reactance. This x is called as transfer reactance. And you have to bring the value of this transfer reactance also to a lower value. If you're having a lower value of this transfer reactance, and if you're having a higher excitation value, it is possible to maintain this del dp by d del in a positive direction. So it will be stable. Okay, and after this, the synchronizing power coefficient, you have to know, they might be asking in 2 marks. It is also called as a stiffness factor. So here you can see, so it is nothing but the value what you the power value after uh, derivative, which is nothing but the dp by d del, what you have seen, dp by d del. It is called as the synchronizing coefficient. It is very important value for maintaining synchronism with respect to the grid. So what you have to do is, you have to write the power equation p equal to eg em by x into sin del, and for this equation you have to take the derivative. Okay, you have to take the derivative. So it's very simple. This is a constant. The variable is only your rotor angle del. So if you are taking the differentiation, it becomes a cos del. Okay, and the name for this will be synchronizing power coefficient and stiffness factor. And as I said, this has to be maintained in the positive direction. Okay. So this is what with respect to your rotor angle stability. There is still your voltage stability. So after that, we will be moving towards your single machine uh, system.